Good afternoon. Thank you for joining our broadcast on enterprise innovation. I'm Matthew O'Keefe, your host. I'm a corporate technologist at Oracle. And with me today is Gary Greider. He is the head, I hope I get the title right here, head of computing at Los Alamos National Laboratory. Gary and I have known each other for quite a few years. When I was working in HPC directly in the 1990s as a school teacher at the University of Minnesota. Gary's been very active in all kinds of research that touched on my work in computing. And we also worked together on a conference called the Massive Storage Conference that brought together researchers and folks in industry and labs to talk about really the largest scale storage systems. So this is a conference that has been going on for about the last 7 years. It continues to be a place to talk about a lot of different kinds of innovation. So with that, we'll go ahead and get our discussion going. So Gary, Los Alamos is a very interesting place. It's where the first nuclear bomb was designed. They brought together a team of the most brilliant scientists probably that may have existed on the planet at any one time. And they focused them on this very specific mission. And they succeeded. And that's basically the seeds of where Los Alamos came from. And now we're at almost 80 years later, and I think Los Alamos continues to be a place where there's a tremendous amount of innovation in, computing and software and how you leverage computers. You guys design your own computers. So I think, maybe we could start with you describing the history of the lab from your perspective, and maybe tie that into how you think about things today and what goes on at the lab.
Okay, sure. So, as you know, the lab invented the nuclear weapon, and lots of famous people. And in our world, the famous people were people like Feynman and von Neumann and the like that were working on providing computing and the physics behind it and the physics that they did with computing. And the lab's been essentially computing since day one. You can't really do science without having computing. Of course, back then it was done by people. So there was a whole large department of women that did, the math department that did the computing on calculators, and then, later on tube equipment that we used in ENIAC, and MANIAC and its follow-ons, and then to IBM and CDC and Cray and Thinking Machines and all the machines we've had since. It's interesting. My mentor at the laboratory, Marge Devaney, she was a computer originally when she came to the lab, and then she was a programmer, and what she programmed it with was wires. So she had a box of wires in the corner of her office that had been to Pennsylvania to ENIAC to program one of the first problems that ran on that machine. So wow. She was an interesting character and definitely an interesting role model for historical computing, at least in the U.S. Basically, we're still in the same business. We're stockpile stewardship for the nuclear weapons complex for the nation. And the bulk of the weapons designs were done at Los Alamos. Livermore did some, but Los Alamos has the bulk of them. And so we're responsible for the warhead design, and whether the thing will work. We're not responsible for delivery or anything like that. That's Sandia's mission. But we can't test nuclear weapons anymore. They're all 50 or 60 years old. How do we make sure they're going to work? How do we make sure they're safe when we roll them around on trucks and when we take them off of submarines and things like that? And we even do dismantlement for other nations with nuclear weapons stockpile as well as our own. And so how do you do that safely without testing it? And that requires a lot of computing to do. So it's always required a lot of computing to do these things that you can't test, or you can't test a lot of. The nation, of course, did a lot of nuclear testing back in the 50s and 60s and even up to the 90s. So we have a reasonably large amount of data to verify our models and things against. So the data is hugely important. But the kind of questions that we ask of of the simulations are getting harder and harder because it's been longer and longer since we tested anything.
Oh, sure.
And so the kind of problems and the problems that were easy to solve were solved long ago. So we're left with the really hard problems of why did this test end up that way? And there's things today in the stockpile testing program that we still can't explain, and we're struggling with how to do that. And of course, you don't know the exact thing that happened. You're trying to recreate something that happened a long time ago, buried in Nevada, and so it's essentially a very, very large physics and statistics problem. But why physics? Well, that's what it is. And then why statistics? Well, you don't know what the right answer is. You're just trying to narrow the error bars to where you believe what the answer is. And you can convince a bunch of scientists that the answer is what it is. And so we have a fleet of statisticians that we use. And we've been doing, the equivalent of what today one would call machine learning for a long, long time. Because we do an awful lot of simulations and try to figure out what the right answer is without knowing what the right answer is.
Yeah, very cool. Yeah, it's interesting. If you look at like the weather people, they really have it easy because they have like daily feedback. They have measurements. They can measure they can pretty much on a very real time, regular basis, test what their, what their models look like. So yeah, that's very. So how did the culture, so the computing culture started with, as you mentioned, just literally manual calculators. Then you took, I believe you mentioned that you took sort of you re-implemented ENIAC in a more practical way. And then can you walk us through sort of how did you go, based on the mission requirements of these kinds of simulations and design, kind of how did you develop the thinking at Los Alamos about what sort of computing you needed and how should you acquire these systems, starting from the, way back in the early days?
Well, so in the early 50s, there wasn't a computing industry to buy from. So we developed our own. John von Neumann and Nick Metropolis primarily did that. And they built Maniac and Maniac 2, which were versions of ENIAC to do math. ENIAC wasn't necessarily built to do math. It was built to do I think tabulation and things like that for ballistics. And so anyway, we built our own because we had to, and wrote our own software, which originally was wires. Because we had to. Then slowly the computing industry began to start, and IBM was one of the first ones, of course, and RAND was the other. And true to form, Livermore and Los Alamos kind of split the world up, and Livermore went with RAND and Los Alamos went with IBM. And we used IBM gear to do tabulation-oriented things, which is what it was built for. And we sort of tricked it into doing math. For years and years, until the Stretch project, and that's an interesting project that happened. The Stretch project, Stretch and Harvest at NSA, and Stretch at Los Alamos, was a project to get a 10x improvement from the original IBM tube gear to the next generation. And we actually built a building designed by IBM to put the Stretch system in. It's still Los Alamos, built in the 50s. And it was supposed to increase computing power, for math problems, by a factor of 10, and it failed. It only got about a factor of 4 to 6, depending on what the problem was. But what's interesting about it was in that failure came the IBM 360 architecture. That's where it came from, was the Stretch project. And so that's how IBM became the 60 or $80 billion behemoth that it is based on that architecture, right? And so that's where that architecture was born, and it was a super interesting project. But so we used that model all along from then on to partner with industry to do things sooner than they might normally do otherwise, or bigger than they might do otherwise, or faster than they might do otherwise.
Mhm.
and fund them to some extent, and try to be synergistic with where they want to go, but a little quicker than they might go otherwise, and the like, to try to service our needs. And we've been at that since the 50s, and that's essentially what we do today. Is we try to partner with companies, the Crays and the HPs and the NVIDIAs and the Intels of the world, and
Yep.
the AMDs and the like, to do those things, right? Put extra instructions in where it's convenient, put extra memory capabilities in where it's convenient, to try to get our job done, easier and better. We leverage what we can, and we pay for what we can't.
But you don't always, you don't just work with the very largest companies. You guys, Lanel also, funds smaller start, even down to the startup level. There's like Panasys, there's Peter
Yeah.
Graham company that built Luster, and kind of on and on. I mean, you guys have been very aggressive about working really flexibly and thoughtfully with these kinds of companies. So that's something that really impressed me. Can you speak about that just a bit? How you think about that?
Sure. That was kind of all started with the ASCII program, which was the roots started in 1993. It began in earnest in 96. And that was a response to the 1992 Test Ban Treaty. The Test Ban Treaty said we wouldn't do testing anymore. U.S. didn't sign that, but we obey it. And so it had been a number of years since the Test Ban Treaty had been signed, and we hadn't done any testing. And people were beginning to get worried about, how long is, the people that witnessed the first tests were starting to die. They were that old, right? And so the knowledge base was about how the weapons worked and how well they worked and how the tests worked and all that kind of stuff was disappearing, right? And so this program was started to try to codify that knowledge into application code. That's essentially what it was trying to do. So we were trying to codify the knowledge base that was disappearing rapidly into 3D models that would, produce the same thing that somebody's mind would produce a long time ago, right? And so, and the thinking was that we would need a massive amount of computing compared to what we had in the past, because the computer was going to do it all, more or less, with input from the human, as opposed to humans using blackboards and just using computers for rote things. And so that it began. So we began this march to get to a 100 teraflop computer, which in '93 was big, and we put a 10-year roadmap together that we updated every year, and we essentially had these things called curves and barriers, and the barriers were, what things do we know we're going to run out of gas on 5, 6, 8 years from now? When do we need to start funding things to cover those bases? And that's exactly where Panasys and Luster came from, and Infiniband. And there's a whole bunch of things that we paid for. Most people don't know we paid for them, that they were paid for, and they were started, sometimes as much as a decade before we actually needed them, because sometimes it takes that long to do. Most of the interconnects that were out in the world in that time frame were paid for by us, because we couldn't pay for just one, because one's a bad number. The company can go out of business, whatever. So generally, there were 2 or 3 options that were funded, and it was an ongoing thing for 20 to 25 years that we looked out ahead 10 years and said, what are we going to need 10 years from now? It's not going to happen by itself.
Right.
And we planned for that, and we put that in our mortgage budget for how much when we were gonna start it, and how long it would last, and all those things. And collaborations were, the labs were put together so that they weren't off doing their own thing. They were doing things that we wanted them to do. So it was very deliberate, very planned out funding mechanism for staying ahead of what we needed in computing, and we still do that today. It's just done less formally.
So oh, I'm sorry, excuse me, turn my phone off here. Wow, sorry about that. So what you're saying is basically that you had Los Alamos had sort of specific objectives based on the requirement, which was you had to be able to monitor the nuclear weapons stockpile, make sure that the designs you were supporting would still function, and so the computing requirements kind of were based on that. And then you Yeah, and then you were able to, and then you kind of looked at targeted technologies, interacted with companies and innovators out in the field that could deliver that. What kind of staff do you need to be able to do that? How do you build staff at Los Alamos? I mean, you're kind of almost, I've known each other for quite a while. You're kind of a combination of somebody who can, help a big organization function. At the same time, you're incredibly hands-on, very aware of the technical details. How do you think about building the organization, and maybe what's the culture at Los Alamos in terms of people, et cetera, to support, this kind of work?
Well, the culture, the people culture is incredibly diverse, because in order to do, to build something like this or test it or whatever, there's lots of disciplines involved, right? We have more physicists than any county in the U.S. We have, more mathematicians than any county, north of the Mason-Dixon line. All these things that you have to have, right? Engineers, chemists, heavy metallurgists, and all kinds of people. So, it's a very diverse community, because to get that kind of population of top people in those kinds of areas, they have to come from everywhere. Also, Los Alamos is a very remote place. It was very remote back then, and it's still not. It's still pretty remote. So recruiting people to a remote place isn't necessarily all that easy either.
It's a nice place, though.
It's a nice place. Yeah, it's 8,000 feet in the air, and there's mountains around you, and there's trails and all that kind of stuff. But there's not a lot of nightclubs. So at any rate, we have the largest student program in the DOE complex by about a factor of 3. Okay. So we have an enormous student program. So the laboratory is about 12,000 scientists.
Wow.
And we have the population of students typically in a year is 1,900.
Wow.
So 1,900 students come to Los Alamos, either real or virtually, every year into a town that's 20,000, right? Yeah. So 10% of the population of town is a student population.
That's amazing. I wasn't aware of that.
Yeah, 400 postdocs, and I mean it's incredible.
Okay.
And so fully 2/3 or thereabouts of our population came from our student programs.
I see.
And so the student programs are incredibly healthy. We have summer schools and all these things that try to attract people to our problem set. And even if they don't come back to Los Alamos, sometimes they go to industry to help us, right? So they're so interested in the difficulty of our problems that they'll go to work for HPE or Cray or Intel or somebody, and that's okay with us. I mean, as long as they're still thinking about our problem set, at least for a while.
Yeah,
that's value. So we certainly don't hire 1,900 people a year. We have been hiring, close to 1,000, but our culture is really academic and really based on the student program. It's a huge deal.
Well, I think the advantage there is you get, when I was teaching with the University of Minnesota, one of the nice things about youth is, they just come in without really they just, they have, their brains are fresh. They're not locked into specific modes of thinking. And so really have the freedom they have more degrees of freedom than we do. They don't know all the things that we know, but they can come at problems in ways that, that you might not otherwise think. Like, for example, the whole STEP project. When I was sort of first exposed to STEP, I was really blown away. It was like, I'd never really thought of, thinking of something quite that distributed with local control. So I think that's so having all that youth coming into your company obviously really help.
It goes beyond the student program itself. SEF, for example, came out of a university funding activity.
Yeah.
And we fund, CMU, PDL, and interesting things that come out of there. And so, we probably spend $30-40 million a year on university contracts in the computing area alone. Yeah. To try to just seed centers that are good at things that can develop things that we'll use someday.
Yeah, and it's interesting. One of the physicists I collaborated with when I was at Minnesota Paul Woodward was, he worked closely with folks at Los Alamos. So he was a numerical, design numerical methods that were useful there. And so so NSF funded him, but you guys funded him, and again, very world class fellow.
Yeah, neutron guy, that's for sure.
So, I want to dig in a little bit. So we're talking about some of these new technologies developed. You mentioned the IBM 360 is kind of deriving really from the Stretch. So that's a huge impact, because that really defined how you do a computer architecture. Because the 360 was really one of the first. It was actually the first architecture, right? So you had a single instruction set and then multiple different physical implementations off that single instruction set. So of course we all sort of take that for granted now. Then I think the CDC 6600, which was something Seymour worked on before he built the Cray one that you guys consumed. I don't know if the lab used the 6600, but a lot of the kind of like fast forward 25, 30 years, it's what you found in microprocessors. So all the prefetching and registers, et cetera, was there. So there was really, I think the base computing, a lot of that was really, I think the labs can claim some credit for a lot of what happened there.
Yeah, we had tons of 6600s and 7600s. And I was looking on the internet the other night, and I had been reading. We did this history project where we're capturing our computing history, and I was reading about Hydra. Hydra was our storage area network back before there was such a thing as a storage area network. And the way we built it was we had a whole fleet of 6600s, and we wanted to share peripherals between them, sort of the definition of a storage area network. And so we bought another 6600, and we rewrote the operating system to make it be able to share peripherals. So it was a network.
Yeah.
The computer was a network because there weren't networks, right?
Right.
And we hooked up all the tape drives and disk drives to that one 6600, and the rest of them shared them through that machine. And I believe that was the first storage area network, which had to have been 71 or something like that. And way before Fiber Channel and the like. And actually, if you go look on Wikipedia, what's a storage area network, it talks about things in the 90s, but things like that existed in the labs long before that.
That's really that's very interesting, because I think that particular machine, there's so many firsts, it's kind of like mind-boggling. And then I think when Seymour went to the Cray one, he added vector registers and a few other things, but a lot of the original, a lot of the original innovations there kind of went forward in the Cray one. So, and then also Infiniband. So Oracle built Infiniband into our Exadata database appliance. So we've been using it really for quite a long time. It wasn't, HPC was aggressively using Infiniband for quite a while. And now I think it's again starting to go more mainstream. But what was the reason? What was the reasoning behind Infiniband when you guys were put some effort into that?
Yeah, we put effort into it, as well as we had a partner in Oracle. The first time we had a partner in Oracle, and actually the banking industry as well. So why did we do that? So we had funded interconnect technologies that were proprietary for IBM. We funded the IBM one for the SP1, SP2 family.
Oh, I see.
We funded Quadrix for what at the time digital equipment, which became HPE. And we had funded 2 or 3 or 4 of these proprietary ones. And we were getting sick and tired of funding proprietary interconnects for every company that we wanted to bid on and buying a supercomputer from. And so we said, hey, let's build an open source based, interconnect that anybody can use. And of course, at the time, PCI hadn't come out yet, but there were microchannel and other kinds of, architectures that for IO buses. And so that's where it came from, is us being just sick and tired of funding everybody's favorite, proprietary interconnect.
Of course.
And we said, let's not do that. Let's have 1 or 2 that everybody uses, and we can innovate that way. And that's where it came from.
Oh, I see. Okay, very good. So, one of the things I wanted to talk about was open source software. So you guys have funded a lot of different, some of the projects you funded were open source.
Mhm.
Obviously, you leverage open source in a lot of different ways. It's part, it kind of came to mind when you talked about Infiniband, because it's kind of something where you can build a community, or you can build some standards and community around it. How are the labs thinking about open source these days? Obviously, I think it's something that continues to be powerful that you can leverage. It's obviously of interest to enterprises as well, great interest. So what are your
Mhm.
thoughts there?
Well, so it's codified actually in the way DOE funds the labs. So most people probably don't know this, but the ASCII program was a big uplift in money to for computing at the laboratory. But that had to be based in some economic thing.
Mm-hmm.
And so the thing it was based on is a bill that predates it called the America Competes Act.
Mm-hmm.
And so there's a thing called the America Competes Act, which says that things in the federal government that are associated with the America Competes Act need to help U.S. industries be better. And so at the heart, at the core of the ASCII program and essentially NSA computing, DOE and NSA computing since then is the America Competes Act.
Okay.
So we are required by the way we're funded from Congress to open source anything we can
Okay.
and work with and not go develop everything ourselves, but work with industry to develop things for us that are useful to them and us.
Mm-hmm.
We could go build our own everything, but that's not the way we're funded. And so it's a requirement for us to do that. I think is also I think it's a good thing, and we've made good use of it.
Sure.
But it's at the core of our funding mechanism.
I see. Okay. Very cool. So I wanted to ask you a bit about, so you talked a bit about the weapons mission, the specific mission at Los Alamos, which is, helping maintain the nation's nuclear stockpile. Could you tell us about how that shapes how you do computing? Because I know, just listening, from having spoken to you before, you guys have a different sort of profile than, for example, Livermore, or as you mentioned, Sandia or Oak Ridge, for example. So how does that frame, how you run jobs? How many different types of jobs do you run? What's kind of different with the other labs? Could you tell us about that?
Sure. So first, there's two parts of the DOE complex for laboratories. There's the nuclear weapons complex, which is Los Alamos, Livermore, Sandia, and then there's all the other national labs: Oak Ridge, Argonne, LBNL, Jefferson Labs. There's a bunch. I think there's 17 actually.
Mm-hmm.
That are Office of Science. So DOE Office of Science laboratories are laboratories, and their missions are do great science in the name of energy.
Mm-hmm.
I mean, that's literally what their missions are.
Mm-hmm.
And so they're quite broad. Their mission is pretty fatty, right? It's whatever science needs to be done, this time, and it'll change from time to time.
Sure.
They're not based in some long-term decision support mechanism like we are. The weapons program is based on a decision support mechanism for the weapons complex and stockpile. And so you'll find the Office of Science laboratories buying for that thing, right? They'll have lots of codes. They have lots of users. Anybody that can do good science in the name of energy can write a proposal, and if they're funded, they can get time on those supercomputers to run them. So the breadth of what they have to run is enormous. Mm-hmm. If you look at NERSC, it's incredible. At LBNL, it's like 4,500 codes. Wow. I mean, it's a lot of codes, right? Yeah. And 10,000 users or something. And so, and Los Alamos is on the far end of the other end of that spectrum, which is we have maybe 100 users and 4 codes. Okay. And so, it's an order of 1,000 less. Right. And even within the weapons complex, the Los Alamos, Sandia, Livermore lab complex, we have different missions. So Sandia's mission is weapons engineering, right? So how do you build delivery mechanisms and things like that? And the engineering around, neutron tubes and other kinds of things that are required, but not part of the nuclear pit itself and how it works. And then Livermore and Los Alamos, of course, Los Alamos came around first, and then Livermore came up because Teller wanted his own laboratory, and because there needed to be what they thought they needed to be, competition between the laboratories on designs. Mm-hmm. And um, and so Livermore has some designs, although they don't have any active in the weapon in the complex now, but they had some. And Los Alamos had a lot more because they were older. And we have all the active weapons today were designed at Los Alamos.
Mm-hmm.
But so that means that the Los Alamos and Livermore missions are really quite different. Los Alamos mission is to try to explain potential weapons performance things and weapon safety things that might occur, um, you know, if we have to use them or if we have to move them around or whatever.
Mm-hmm.
And Livermore's mission is peer review, so they do an awful lot of statistics. So they'll buy a machine, and they'll buy a very large machine, and they'll run jobs that are say 10 terabytes in size, and
Mm-hmm.
they'll run thousands and thousands and thousands of them, and they'll do statistics on the output of that.
I
So
see.
they're running tens of thousands of small simulations. Los Alamos, as the exact end of the other end of the spectrum, will buy a machine, say 20,000 nodes, and will dedicate 10,000 nodes of that machine for the entire life of the machine, perhaps 3 or 4 years, to one problem. So one problem running on a petabyte of memory across 10,000 nodes for 4 years. That's not unusual for Los Alamos at all. So we tend to buy different shape machines because of that. Livermore buys machines that are very big nodes so that they can just a job will run on one node or very small number of nodes. Oftentimes GPUs and the like. Los Alamos, the other end of the spectrum, we would never do that because we know that we're going to have to run across all the nodes anyway. So we'll buy lots and lots and lots of small nodes to get a lot more memory bandwidth of the CPUs.
Sure.
Not many GPUs because the thing is so we had to, it's the problem we actually run is 2 orders of magnitude or 3 orders of magnitude cut down from what the real problem is. So we do these representations that are very, very inflexible and very, the memory references are just all over the map. There's no serialization to it at all.
I see.
You never know who's going to access what. So it's a very N-to-1 kind of problem.
I see.
So the architecture that we build is different than Livermore, and same for them because their missions are different, which is why you'll see us, buying pretty radically different stuff.
Mm-hmm. And then the way you buy has kind of changed over time because you used to kind of go to the vendors and you gave them like specific, you have to have this many flops and you have to have, certain, like metrics that were pretty granular down at the kind of like the computer hardware level and software to a certain extent. But I think you've kind of changed. Has that evolved over time? How you purchase the machines and how that drives? Yeah,
it has pretty radically. We used to buy using specs like that, how many flops and how many bytes per flop and how many bytes per second per flop and all that kind of stuff. And we've stopped doing that, and the reason why is because all the units became pretty silly. They don't represent the problem very well. Flops work. That if your problem is highly aligned memory references, then flops matter. If it's not, then you'll never get all the flops. It doesn't matter. You might as well talk more about the memory bandwidth or the memory reference patterns or the number of messages per second. So for every kind of problem set, there's sort of a different set of specs that might matter.
Mm-hmm.
And we decided to go away from that altogether. And we do this thing we call SSI. I don't remember what it stands for, but essentially it's a suite of applications, of many applications, small applications that in some way represent the suite of applications we really run. And we publish those. Those are they may be export control, but they can be given to vendors.
Okay.
And they haven't changed a whole lot
I
in
see.
a while. They are given here's the typical inputs and outputs for these problems so that you kind of know roughly how big things are going to be. So how much IO you're going to do, all that kind of stuff. They're told how much of each one of those mini apps would make up a typical work for us.
Sure.
So then their job as vendors when they bid on these things is to try to get the most number of those things through a machine in the 5 years it's going to be at Los Alamos.
I see. Okay.
And so they write a proposal that tries to convince us, after doing simulation and all kinds of emulation and the like, to try to figure out what they would bid to us and what they would build for us that would get the most through, most of that science through a system in a
Mm-hmm.
period of time. And we have to take the bids and try to figure out, if they were right or not, and which one's the best deal and the like. So it's
Sure.
purchased not by flops or anything like that.
Yeah.
Now, we do say we need X amount of memory. Why? Because the problems have to fit on the
Sure.
machine. We
Yeah.
do say you can't go above 30 megawatts or 40 megawatts or whatever it is,
Okay.
because we have to power it. We do say that it can't be bigger than an acre or something, right? Because that's all the space we have, right? So there are some hard requirements, but they're really simple.
Sure. Mm-hmm.
And the rest of it is very subjective and based on these applications and their workflows and how well they can convince us they can make those go faster and better and more of them through the machine.
Sure. Yeah, and I think that's a fantastic approach because for years people the industry was, in my opinion, sort of overly focused on a specific benchmark, LINPACK in particular, and so there was a certain kind of structure to machines which emphasize certain things, and frankly it was just a lot simpler to get performance out of a raw machine with LINPACK versus something that was more representative of a big application. But to run a big application, your enormous million lines of codes applications is asking, that's going to be too complicated, plus the security issues. So yeah, that's a really good kind of middle ground for you. So basically, the other trend that I know you've talked about is using these representative benchmarks that really are driven, that really help you understand how a machine could potentially perform for your own your real applications. But one of the trends you've also observed is the kind of the balance of computing and storage and networking inside your machines over the last several decades. Could you talk about that a little bit?
Sure. There's been several things that have happened in that space. One is, before Flash existed, there was disk, and disk was priced to be cheap per byte, but not cheap per byte per second, right? And so, but unfortunately, because of how fast we needed the I/O to go, we ended up buying storage for bandwidth as opposed to buying storage for capacity, which turns out to be a really expensive thing to do, especially with disk. And so, it's all been, when you build one of these machines, it's all about how much science can you get through it. Okay. And if the I/O is the bottleneck, then you need to spend more on I/O. And if the memory is the bottleneck, then you need to spend more on that. And that's changed over the years, but certainly the processor piece of it has become easier and easier and easier for enough of that on site.
I see. Mm-hmm.
Getting enough memory has been okay. It's certainly gotten denser over the years, but getting enough memory bandwidth, we're nowhere close. We're orders of magnitude off. Yeah. And with file systems and with storage systems, we've run the gamut. We used to spend an awful lot on them there for a while. We spent less because Flash had just come out. Mm-hmm. We were able to use Flash for the bandwidth part, and now it's getting more expensive again because the memories are getting so big that, and the amount of storage you have is related to how much memory you have.
Sure.
And networks are similar, right? We've had times when we've spent, maybe 5% on the network, and I would say now it's probably closer to 15%. Those things are driven by economics and pricing voodoo and stuff like that. So it's hard to know really, what's real and what's not in that space. But what we end up paying for different parts of the machine has changed so much over the years and seems to ebb and flow based on where things are at in other industries and whether other industries are picking up the bill and pushing technology or not and the like. And the cloud, frankly, has helped us there with networks. So our networks are getting cheaper, and the reason they're getting cheaper is because the cloud people are demanding it.
Oh yeah.
And so, we do leverage those people where we can, at least.
Yeah, but you don't. Do you put any of your workloads? I don't. I would assume you're not using public clouds, just be given the sensitive nature of what kind of the calculations you do, or are you able to leverage public cloud for doing something like a bursting, or is it something you've considered? Again, the security would be fairly,
We
might be an issue.
we've considered it, and the
Mhm.
government has funded a couple of the cloud vendors to do secure clouds for them. So we
Mhm.
could use cloud. The interesting thing about cloud, sort of the first fundamental thing that you have to understand if you're going to use it or not, is, are you in a situation where renting would be better than buying?
Sure.
Right? I mean, that's sort of the fundamental question you got to ask yourself first.
Hmm.
And I'm in a situation where I couldn't buy enough computing if I had to. There's
Sure.
no,
Yeah.
there's no way my budgets could go up enough to buy enough computers to make the weapons program, the physicists, happy. And so, in no way, shape, or form am I in a rent situation.
Yeah.
Um,
Yeah.
there's a 2 or 3 week backlog to get a job run.
Sure.
It's so. So we've considered it, and we certainly consider it and do use it for other parts of the laboratory. But the actual bread and butter weapons calculations, it just really doesn't make any sense because
Sure.
you
Yeah.
know you can't move petabytes around that quickly remotely, and um, it's simply a buy is still cheaper than rent
Oh yeah.
uh, because
You're
it's not
actually.
it's not bursty. It's
Yeah.
2 or 3 orders of magnitude too little all the time.
That's right. So you're using your machines 99.999. Your utilization's 99.9999%. So yeah, and I think you do that over long periods of time, right? Because when you'll
Yep.
order, I think your procurement cycles they were either a decade or like I think you start 5 years. Could you kind of walk us through the timeframes when
Sure.
how you acquire machines?
Sure. So we start the process of justifying why we need it about 5 years before we get it, and
Hmm.
so that goes through the government mail of justifying why you need something and how big you need it to be and what you're going to use it for and all that kind of stuff. Um, in general, about 4 years in front of the delivery, we start talking to vendors about technologies that we think that are going to be available 3, 4, or 5 years from now,
Okay.
and what aren't going to be available and what we might want to fund to make them available so that we could get interesting things for us.
So this, just sorry to interrupt, but so this 5-year cycle, what it drives, and that's kind of where you and I have interacted, and professionally, is you're always out there scouting. From what you're always scouting what's going on with storage technologies, what are the trends,
Mhm.
what's going on with compute, et cetera. Right? Is that
Yeah.
correct? Yeah.
So then generally there'll be an RFI or some sort of request for information about 3 years out.
Okay.
And then 2 years out, there'll be an RFP and probably a placement. And then we'll start paying non-recoverable engineering costs for things that we want to have developed that
Okay.
we need to either show up on the machine or show up a year after the machine or something like that. And
Is
the
this?
machines typically last about 5 years. So it's about a 10-year cycle from inception to destruction.
Mhm. What are the trends? I mean, what are you seeing like as you look out like kind of the next 5 or 10 years, and what changes from what you've done before with machines? What are you telling vendors? Do you think the DOE is going to be looking for? What's the future look like?
Well, that's interesting. So Livermore is taking one tact with that. They're betting heavy on leveraging the trending markets, AI and ML, and because those are heavy compute kinds of work.
Yep.
However, they're not. They're very locality oriented kinds of work. So but that suits their need, and so they're really pushing hard to leverage that trend and that set of technologies that are coming out of that market, which is great. If you can use that for your problem, it's great. We're actually trying to leverage a different phenomenon, and that is the tailoring market. So, you know, uh, Apple, they have an ARM processor and they tailor the hell out of it. It doesn't look like an ARM processor when they get done with it. It looks like an Apple processor, right? But it
Right.
started out as an ARM, license, right? And so where we're headed at Los Alamos is to try to tailor processors and memory subsystems to do what we want.
Nice.
And so that's a completely different thing to leverage, right? It's not
Yeah.
leveraging a trendy industry application. It's leveraging a trendy industry, hardware application,
Yeah.
phones, all that kind of stuff.
Yeah.
And so that's what we're doing. And we've been involved in several ARM-related efforts that you've potentially heard about.
Mm-hmm.
And the memory subsystem is also incredibly vital, important for us because memory bandwidth and memory latency governs our applications way more than the processor. And so we've been partnering a lot with the memory vendors to try to change our life there.
Yes.
And so I think you're going to see, memory. Well, you're going to see 2.5D and 3D integration become mainstream, which is going to cause memory bandwidth to jump by a factor of 5 to 8.
Okay.
Which hasn't happened ever.
Yeah.
That's an interesting stair-step function that's kind of never happened.
Yeah.
Unfortunately, then it gets back on a curve again, but it is a huge stair-step function. So you're going to see that. And I think you're going to see tailor. I think people are going to realize that you can tailor and help yourself if you know what your applications need. And so Los Alamos is kind of the only national lab in the US that's doing this, but the Europeans and the Japanese are doing this pretty heavily.
I see.
And so, we're sort of following and or partnering with them, and the rest of the national labs are going the other route, which is leverage, a hot application area. And you have to leverage something. You can't afford to do it all yourself. So that's sort of how it's come out.
Yeah. Are you guys going to be working down at the granularity of like cache designs, or potentially looking at, like certain kinds of, what Cray used to do with vector registers, against arrays and that kind of,
I think the way to think about it is maybe custom scatter gather.
Okay. Mm-hmm.
Maybe one-sided operations that might help us a lot.
Okay.
That, where the memory controller might be on the memory stack itself.
I see.
And you do a test and set or a compare and swap or whatever.
Sure.
And have it do it at the memory, so you save 2 trips, back and forth and the like.
Okay.
And if you do a lot of that, you save a lot of time and effort and energy and money, and the application goes faster and so forth. So, and those are kind of simple examples. The other things that we're doing,
yeah.
Well, we're trying to do computing near memory, near storage, and computing in the network where it makes sense.
Okay.
That's becoming very practical because there's a processor on everything now.
Sure.
And you can figure out a way to leverage it. You can help yourself. So it's not really dark silicon, but it kind of is. You're lighting up silicon to do something that it's sitting there and it's not doing anything potentially, or it's not fully busy. And you can find a way to leverage that. If you're moving data, you might as well do something to it while you're moving it, right?
Yeah.
If you're storing data, you might as well do something to it near the storage as opposed to moving it all the way across the network and so forth. And so those kinds of things, we're going to be doing a lot of that kind of thing. It's tailoring computational storage, tailoring computational network, tailoring computation near memory.
Very cool. Kind of thing. Yeah, very cool. Actually, so Oracle with Exadata, what we do, we actually have, we do calculations in the storage servers. So if you think of SQL, of course, it's basically, it's equivalent to vector operations on tables. And so you have like a very large query or some kind of operation you're doing across a very large table, we'll partition it up across these storage servers and then just do that locally to the storage servers without bringing it back to compute. And so it can be very powerful. And then I think also to your point is just with graph processing is becoming more and more popular with our customers, especially in the financial industry, because they can use it pretty effectively to catch fraud. If they find these sort of circular loops of financial transactions that shouldn't be there. And again, that's, to your point about scatter gather and having, sort of memory systems that can support that. That kind of functionality could be very useful, not just with, or our specific product, but everybody doing graph processing. So yeah. I think labs, there you go. The labs, I think, again, are going to be, you're going to continue to push the industry in directions that are actually very helpful to all of us. So yeah, very cool. So before the call, you and I were talking a little bit. One of the things that I noticed in my HPC career, that part of my career, is that the most effective groups, teams, that in terms of what I can think of as innovation. So they're on the cutting edge. They have the best weather forecast. They have the best, they have the best, ability to work on nuclear type problems. There are kind of two things, and I bring this up partly because I spent some time with the Europeans they have a weather center called ECMWF, the European Center for Medium Range Weather Forecast. So it's actually one of the first labs to do like a 10-day forecast of the weather. So that's called medium range. Back in the day when they started, I think it was in the 70s, probably in the 70s, I think. The computers were fairly primitive, and they, like you guys, like Los Alamos, they had to do cut a lot of corners and really work hard to leverage that. And then that became a discipline that they brought forward. But basically had that very specific focus, best 10-day, weather forecasts, and basically have kept that. So if you look at the scores for weather centers, they've basically stayed in the lead. And so they had that focus, and they had, relatively small teams, relatively, really high caliber teams. And I think there was also a factor of accountability. So if you do a weather forecast, people know if it was good or not, because the weather happens and then you can score it. And I think it's a little harder for you, for folks in your area of research, simply because, as you pointed out, we don't allow bombs to, we're not allowed to do that anymore. But what's your take? I mean, it's a specific problem, number one, kind of performance is measured. What other are those, what other factors do you think of in terms of groups that have, sort of really good records for innovation or really stay at the leading edge?
Well, I certainly agree with you that a focused mission matters a lot, and a small disciplinary group matters a lot. I think for us, the fact that the problem gets harder as you go. So just when you thought you had it, you realize there's 19 more things that you didn't know about it.
Oh yeah.
And that's the way it's been in the weapons program since the beginning, is that there just doesn't seem to be any end to the veracity of the problem space. Mm-hmm. It seems to, and so you don't ever get to stop. If you even think about stopping, you'll already be behind. Mm-hmm. And I think, so that focused problem set helps you a lot. Multidisciplinary small teams help you a lot. But for us, we realize we're still off by many, many orders of magnitude in capability to be able to do things that the scientists really want and need to do. And so, I think also being, maybe in the same community as the user might help some. Yeah. I don't know. I suppose that the cloud people don't have that, but we do. Mm-hmm. And I find it useful that, one of the guys that does the material science for the laboratory is my neighbor, right? And they hear about all the time, why the hell can't I get my jobs done sooner? And I could get a whole lot more science done if I only had a machine 400 times bigger than I have now. And so, and that's interesting, right? I think that the community aspect of Los Alamos is kind of interesting. It's a little different than some other places.
Yeah, that's actually interesting. The Lockheed Skunk Works, that I think had a similar culture, which is, for example, they made the machinists that were actually building the aircraft. They were physically very close to the designers, so the designers would have stuff, and then the machinists would be right there. And so they if the machinist couldn't make something happen with the design, you knew about it right away.
Sort of additive manufacturing before there was a term called additive manufacturing, I guess, right? Yeah.
That's right. That's right. And yeah, and I always found, when I was at university, it was just, some of the most productive times were this with my students were social time. So we'd go on Friday afternoons, we'd go out and drink beer, and that's probably because you sort of let your hair down a little bit. And I think that kind of that. So yeah, there's an advantage to having a sort of an isolated, smaller community way up in the mountains. So
one of the interesting stories is Hippie. I don't know if you remember Hippie. It was a high performance parallel interface, 100 megabytes per second, which in the early 90s, that was pretty cool, right?
Yep.
Way faster than Ethernet at the time, and that was invented on the ski hill at Los Alamos. Michael McGowan, they bet one another that they could build a 100 megabyte per second interface with Radio Shack parts on the lift. And sure enough, a month later, they had Hippie going, which was this 100 megabyte per second parallel interface that was Radio Shack parts.
Oh, yeah. I remember we were working when I was at Minnesota. We were working with Silicon Graphics really closely, and so we built an array of Los Alamos had an array of their big multiprocessor machine, the O series, and we put together like a huge cluster at supercomputing, and the Hippie cables were like 2-3 feet thick, because remember how those cables were so incredibly thick. So good times. 25
wires.
But you're right. It was basically dirt simple. Hey, we got about 5 minutes. One of the things I want to go back to something you said earlier, because it's something that I think enterprise, I kind of live in the enterprise IT world now, but it's when you mentioned you funded multiple projects, right? So you had, like, for a file system, cluster file systems are such a demanding, difficult project. I mean, I think in terms of like failures, cluster file systems is like one of the number one highest percentage of failures. So I know you funded Luster, you funded Panasys, you funded Gluster and Ceph. So you actually hit most of the successful ones, actually. And that's a very good mindset. In my opinion, it's a great mindset, which is most of the time enterprises say, let's make one bet. We'll make one big bet on one thing, and there'll be one team, and then we're going to make it work, and it can't fail. And it's like, and then I see these same projects fail so often. So they might say, well, if you split, you're splitting up your resources across too many projects. What's your take on that? Why do you do that?
We do that because we've made a commitment that we'll get something to work at some scale by some amount of time, and failing kind of almost isn't an option in a way, right? So you have to do that, right? And I find that interesting that you said it that way. We did fund more than one, but even within each project, if we knew that a particular part of it was going to be thorny, we would allow them to fail a couple of times.
Okay.
So, for example, Luster distributed metadata, we allowed them to fail twice before they got it to sort of work. And it still isn't not perfect, but
sure, yeah.
And the same thing for Ceph, the Ceph file system, the file system piece of it. They took more than one run at it, and they got Rados to work, which is a block thing, right?
Sure, that's right.
The file system itself was much harder. It came along way later, and the reason why it came a long way later is because it had some failure along the way. I think we're pretty good at that, and I think we're pretty good at that because it's kind of cliche, but failure is not an option for us. We're the last defense between nuclear weapons that go off in the wrong times or not, right? So
that's right.
Make it work. And we had the luxury of being able to fund it all, although none of it was funded, as much as we wanted. But
sure.
That I think that you can't fail thing really drives your, the way you think oftentimes.
But it's interesting because basically it's ironic because you had you actually have a tolerance for localized failure. You just don't want a global failure to happen, but you'll tolerate local failures that, to your point, it's like, hey, I'm not going to shut down this Luster attempt at distributed metadata because that's a really, really hard problem. And I'm going to let them make multiple runs at that. And I'm trying to remember, there was a middleware type problem that you were funding over the years. I was kind of observing this problem. And frankly, I'm trying to remember who solved it for you, but I marveled at your patience, because it's sort of like, that's a really hard freaking problem. And then eventually, our friend at CMU got it. So Garth basically, his team got it. I forget which, it was like a middle, I forget, it was some part of the middleware problem. Doesn't really matter. It just gets back to the point about having that patience, being willing to try different things. And it's rare in enterprises, I have to tell you something, because basically if somebody commits a lot of money to something, it's just assumed it's very CFO, very financial driven. If it fails, it's assumed you've wasted that money, rather than, oh no, you haven't failed. You just made an investment in the ultimate solution. That's not the mindset.
That's actually interesting. That's probably the hardest cultural thing for the young people that come to the lab to get.
Mm-hmm.
It's not somehow not been driven into them that localized failure is acceptable. In fact, encouraged oftentimes. And I don't think many places you go to work it's that way. And I think this, you can't fail, really drives it. Did we freeze? Are we there? I think maybe we froze.
This function, this chat to tune. Do you have any other, any final comments or observations you want to make before we wrap it up? About
Not really. I got to head on to my next meeting, so
no
unfortunately.
All right, very good. Well, thank you again, Gary. Again, Gary's the head of computing at Los Alamos National Lab. He's been very insightful today, very helpful. So thank you, and maybe you'll join the show in the future. Hope to see you again. Take care.
Okay. Thank you. You too.
Thanks a lot. Thank you, everyone,
Bye.
for joining. Bye now.